Hello and welcome to Lecture 9. Today I'm going to tell you what a basis of a vector space is. But before that, I kind of want to give you a little bit of a motivation. So first of all, let's get back to our gamma function. So let V be a vector space over R, and let alpha equal 1v1 through vn be an n-tuple in V. Then we have this function gamma alpha that goes from Rn to V and sends a vector lambda 1 through lambda n to this linear combination. Okay, and so far we have looked at these linear transformations and we have asked ourselves, well, one, is it injective? And then the answer is when alpha is linearly independent. And the second question was, when is gamma alpha surjective? And the answer to that question was that when alpha spans V. And so now we want to put these two together. So this implies that gamma is bijective if and only if, well, alpha is linearly independent and alpha spans V. And so this will be an important notion, so we're going to give this another name. But before we do so, let me tell you why is this an important notion. And so the idea is a little bit, and this way we kind of want to coordinateify V. So the idea here is so I have to write I'm just trying to not write it incorrectly. Coordinateify V, yeah? So what does that mean? Okay, so if gamma alpha from R to the n to V is bijective, then I can somewhat identify one element of V with one element of R to the n. Then one element in V corresponds in Rn. In fact, we can identify V with lambda 1 through lambda n. Sorry for this little thing here. Where V is written as, well, lambda 1 times V1 plus all the way up to lambda n plus Vn. Yeah, and so this being bijective, this map being bijective, means pretty much that there's only exactly one way of writing V like this, and also that I can write V like this. So there's two things to this. So being surjective means every V can be written as a linear combination in this way. And being injective means that there's only one such way of writing it. Yeah, and so I can pretty much go kind of back and forth between elements in V here. So we take our element V in V. Well, we identify it actually with something in R to the n. And this goes towards this direction of thinking that actually, if we do have a vector space that has a finite set that spans it, then you can actually think of this vector space as an R to the n, and precisely via this identification map gamma. So via gamma, I can kind of go back and forth between an Rn and the vector space V. And so this will be something very important coming up later. Okay, that then before now we do any further, let us give tuples that are linearly independent and spanning sets a name, because this is a very important tuple. And so we're going to call these things bases. So a tuple of vectors in a vector space V is said to be a basis if, well, it spans the vector space and on top of it, it's linearly independent. So let us start out by giving some examples. Let's go to R to the n, the one we know the best. So here, the standard base is just taking these vectors ei for I from 1 to n. Now let's go to the polynomial of degree as most n. Here I can take the set 1, x, x squared, so all the monomials. So I'm just trying to like go through all the different ones we've seen so far. What is another one? Well, the matrices. So consider the set of n times n matrices. And so now I'm going to write something that looks a little complicated, but what you should really just think of it is we're going to name all the matrices that have exactly 1, 1 somewhere. So one of the entries is a 1, and all the other are 0. So now here let's, so we take E11, E12 all the way up to E1 n, then E21, E22 all the way up to E2n, and then all the way up to EM1, EMN. And so where Eij, okay, so I take the matrix Eij and I look at the entry St is equal to what? Well, I want it to be 1, 1 and zeros everywhere else. And so the 1 should be precisely when this index coincides with this index. So if I is equal to S and, so this and is important, J equals to T and 0 otherwise. So I hope that this notation here is known by everyone. What I do mean here is the ST entry of the matrix Eij. And in this case, we have that S runs through 1n and T runs through 1m. Okay, and let's do a last one. Let's look at the trivial vector space. Then the empty tuple is a basis for the vector space that can just consist at 0. Okay, so now let's go to our first result on a basis. And so this is the result I kind of hinted to beforehand. So what does it say here? If you have a vector space and you take an n tuple in that space, then this is a basis if and only if, well, for each element in that vector space, there's a unique choice for these coordinates. Yeah, so there's a unique way of writing v as lambda 1 through lambda v1 plus all the way up to lambda n bn. Yeah, and so this goes back to the motivation we had at the beginning, where we said, well, we want to characterize when this gamma is bijective, and it is precisely when the tuple you were taking is a basis. So let's try to prove this. It is an only if. It is an if and only if statement. So as we've learned we have to do both directions. So let's do this direction first. So in this case, we suppose that V is a basis for, oh sorry, not that V, of course, that V1 through Vn is a basis for V. And then, well, now we want to do this, there exists a unique. So what do we have to do? Well, we have to show it exists and that it's unique, as we've learned before. So let's start with existence. So what do we have here? We have that this tuple is a basis, and by definition that means spanning and linear independence. And you can see how one of them, so spanning, will be directly connected to the existence, and then linear independence will be directly connected to uniqueness. So existence is pretty easy because as V1 through Vn spans V, we can conclude. Yeah, because spanning really means that every element can be written as it, which is what existence says. Okay, and so next, uniqueness. So there's a little bit more to show here. So how do we do uniqueness in general? Well, we suppose there's two ways of writing it, and then we want to conclude that the ways were the same. So suppose there are lambda 1 through lambda n and mu 1 through mu n. All of these live in R. And so they're going to be such that, well, first of all, I can write V as this linear combination with V1 through Vn and given the lambdas, and also as these mu's. Okay, great. Oops. Then, now we want to do the following. Then we have that 0 is equal to V plus minus V. Well, this is equal to V plus, minus 1 times V. Okay. And so now we're going to use these two different ways of writing it. So the first V, we're going to replace by this here. Lambda 1 V1 plus all the way up to lambda n Vn. And the second one, yeah, so the second one here, we're going to replace by this. So we get here mu 1 V1 plus all the way up to mu n Vn. And you can see here I'm using axioms of the vector space, but we're at the point where we don't want to be so meticulous about it anymore, and we're not going to tell maybe the reader what we're using. We're just assuming that the reader can still follow what's going on. Okay, so what am I doing here now? Well, I'm going to put this minus 1 inside, and I know that this will end up being this here. Okay, and then I regroup, so I want to put all of the ones that involve V1 together. So we have lambda 1 V1, and then we have minus mu 1 V1. And see, like, here I'm quite careful. One thing I want to point out again is that in R, I'm okay to write minus, but in the vector space, I'm not supposed to write minus. Plus lambda 2 minus mu 2 V2, all the way up to lambda n minus mu n Vn. Okay, great. We're here, we got to this point, and now we want to use that the tuple is linearly independent. So we've learned the tuple is linearly independent. That means if I have such an equation here, and let me rewrite the 0 because it's very ugly, much better. So I have here now this linear combination from V1 through Vn is equal to 0. Well, since that tuple is linearly independent, the only way that can happen is if all of these coefficients here, all of these have to be 0. So as V1 through Vn is linearly independent, we can conclude that lambda 1 minus mu1 is equal to lambda n minus mu n equal to 0, or in other words, lambda 1 equals to mu1 all the way up to lambda n equals to mu n, which is precisely what we wanted to show. And so this will give us uniqueness of this thing. And this finishes this direction of the proof. And so now we're going to go to the other direction. We want to show that if we have a unique way of writing each element, then it means that the tuple was a basis. Okay, so we have to show that V1 through Vn spans V and that it is linearly independent. Okay, so let us start with the spanning set. So again, this is the way kind of I like to write things. You don't have to necessarily do that, yeah? I often like to let the reader know, well, span, and when I underline it, I mean, that's what I'm going to show. Okay, this again is pretty easy, and it's precisely tied to the existence, yeah? I say there exists such a way of writing an element, so in particular, every element is a linear combination of that tuple. Every vector in V can be written as a linear combination of V1 through Vn by assumption. Great. And so now linear independence, and this should tie back to the fact that it's unique. Okay, so how do I write, again, good way to think about how do we show something is linearly independent. This always goes the same way. We take coefficients from R, so scalars, and we let them be such that lambda 1 v1 all the way up to lambda n vn, so a linear combination in the tuple we're interested in, is equal to 0. And we have to show that all of these coefficients end up being 0. Okay. And what we're doing now is we're going to use the fact that the trivial linear combination, meaning letting all of these lambdas be equal to 0, actually solves this equation. As 0 times v1 plus all the way up to 0 times vn is 0. And there's only unique such lambda i's. Well, these lambdas had to be precisely these. And there are unique lambda i's satisfying star. So star. Yeah, so I'm basically, let's go back to the theorem, the statement, yeah? So what I have here is, well, I assume that every element has a unique way. So in this case here, I let now v be equal to 0, yeah? So this is star for v equals 0 in the assumption. So then that means that lambda 1 all the way through lambda n had to be already 0. And this finishes the proof. Great. So now we would like to make the following definition. Let me pull this up. So suppose there's a vector space over R, and we want to say that this vector space is finite dimensional if, well, V is the span of a finite set, And otherwise we call it infinite dimensional. And then when it is finite dimensional, we want to attach a number to it, the dimension of V, and we want to say that this is the number of elements in a basis. Yeah, so the dimension should correspond to the number of the element in the basis. There's two problems with this definition so far. So one thing you have to learn in math is that when you give a definition of anything, right? For example, when you define a function, or even if you give a definition like here of some notation, you have to always check whether or not this actually makes sense. Okay, this first part makes sense, definitely, yeah. Either you have a finite tuple that spans it, or you don't. What is more problematic is right now this definition of dimension here, yeah? Because what do we say? We say, first of all, well, it's the number of elements in a basis. But, well, you defined finite dimensional by the spanning set. So the first thing you have to check is that if you actually have a vector space that is spanned by a finite set, then you can actually find a basis for V that is finite. Okay, that's the first thing. And then secondly, and this is even more important, I would say, is that, well, this number here, well, could depend on which basis I choose, right? I can choose plenty, like there's infinitely many bases for a given vector space. So who tells me that if I choose basis A or choose basis B, well, then the dimension, it should not change, right? The dimension is something that is inherent to the vector space. So what we have to show is that that two bases have the same size. And this is going to be our goal for the next lecture. And so this will take us a little while, so we can't do that today. But we're going to prove one last result for today. And this is basically answering the first question. So the first question, whether or not if you have a spanning set there is a basis, this is true. So we'll show that if you have a vector space and you have an n-tuple that spans V, then not only you find a finite basis, but you can show that a subtuple of that tuple is a basis. So first what we do is we're going to construct a subtuple that is linearly independent. So that will satisfy the first part of the definition, and we're going to choose it in a way that it's maximal with the property. And then this maximality should imply that it's actually also a spanning set. So, we want to construct a subtuple let me give it a name, Vm1 all the way up to V mr, V, not W, mr of V1 through Vn that is linearly independent and maximal with this property. Yeah, so what do I mean here by maximal with this property? This means that if I put an element in that, then it becomes linearly dependent. That Vm1, Vmrv with V from V1 through Vn is linearly dependent. Yeah, so whenever I add another one, this becomes linearly dependent. Okay, and so we want to choose this recursively or inductively. So what we do is, well, we go one by one. So first let m1 be the smallest number such that Vm1 is not 0. Yeah, potentially you could have like a bunch of zeros in the beginning. And this is where this result that one tuple is linearly dependent if and only if it's 0 comes in handy. So this is precisely why we proved it for doing such arguments here. So by lemma, and this was 510, Vm1 is linearly independent. Great. And so while possible, we're going to repeat this process, yeah? And by repeating this process, I mean it in the following way. While possible, repeat this process. So I'm choosing M2 such that it's choosing M2 minimal. M2, let me also write M2 greater than M1 minimal such that Vm1, Vm2 is linearly independent, comma, M3 greater than M2 minimal such that Vm1, Vm2, Vm3 is linearly independent, etc. And this process now has to come to an end because, well, we have a finite tuple. At some point, I'm going to get to the end of this tuple. So thus, we obtain M1 less than M2 less all the way up to some MR such that Vm1 all the way up to Vmr is linearly independent. And such that adding any vector from that tuple, it becomes linearly dependent. Any vector v from Vn okay. But this implies then that any v in v1 through vn is an element is such that, let's write it like this, v is in the span of v1 through vn. Yeah, we said that this tuple being linearly independent, this is one of the results from before, makes this to be like this. So this is theorem 5.12. Theorem 5.12 says what? It says that if you have a tuple that is linearly independent and you add a vector making this tuple being linearly dependent, that means that this last vector had to be in the span of the previous ones. Okay, and now we claim that, Vm1 all the way up to Vmr is a basis for V. So it is linearly independent by construction. And so now it's left to show that it's actually a spanning set. So first of all, since the span of Vm1, Vmr is a subspace of V, yeah, because all of these actually come from V, and V1 through Vn is a subset of the span of Vm1 through Vmr, yeah, because we showed, this will go back to what we have said here, yeah. Every element in this tuple is actually in the span. Okay. Now what does this give us? we obtain that what? V, well, V is the span of V1 through Vn, because we assumed the tuple we were given was a spanning set. But this now is contained in the span of Vm1 through Vmr. Yeah, this was one result, and again, I said it was a thing that became very handy, that this subspace here is the smallest subspace that contains V1 through Vn. So since the subspace on the right contains these elements, it has to contain the whole vector space. Okay, and now V is in the span of these, so that means that they span V. Hence, Vm1 through Vmr spans V, which completes the proof. Yeah, so you can always think of it as the following. This will kind of lead you to that conclusion. A maximal linearly independent set should be spanning. And on the other hand, a minimal spanning set should be linearly independent. And so this is kind of the tension between the two. I hope to see you all in the lecture on Monday. Bye.